There's one other thing we need to do because it has been found to be highly effective with ensembles of decision trees, and that's called bagging. And I'm going to require that you also do bagging in your ensemble, because when you have an ensemble of random trees that are trained with bagging, it's called random forest. And random forest has become established as a pretty darn good algorithm, so we're going to do random forest. Okay? Bagging is actually short for bootstrap aggregation. But that's hard to say, so we just call it bagging. And the idea of bagging is this. Each of these decision trees is not going to be trained on your training data. Instead, each of them is going to be trained on a resampling of your training data. So let me explain what I mean by that. Let's suppose this blue rectangle represents your training features, and this blue rectangle represents the corresponding training labels. So you have a whole bunch of features and corresponding labels, and here's what we're going to do to bag. We'll allocate a new matrix of the same size for features and labels, and we'll draw a random sample from this training data, and we'll copy that and we'll paste it right here in our data, and then we'll draw another random sample from our original data, and we'll copy that and we'll paste that right here in our data, and we'll just repeat until our data is all the way full. And once our matrix of the exact same size is full, then we have new data. And what did we accomplish? Kind of absolutely nothing, right? Yeah. Well, we did actually accomplish something, and here's why. Because we resampled with replacement. What that means is, when we drew it, we didn't remove it from the original training data. So it's quite likely that some of the rows will occur 2 or 3 or 4 times in the bootstrapped data. And it's quite likely that some of the rows will be omitted in the bootstrapped data. And because some of them occur multiple times, when you build a decision tree, that'll kind of put a little bit of emphasis on going one way or going another way, right? But you also see that at least on average, the distribution of labels over here and the distribution of features over here is about the same as over here, right? Because it was sampled from the same data. So this is what's called bootstrapping. Yeah, it's just resampling your data is all bootstrapping is. And why do we resample the data? Because it mucks up the data. Why do we want to muck up the data? Because it mucks up the trees. And why do we want to muck up the trees? Because then when they're all voting, they're kind of seeing different perspectives of the same concept, and that makes the ensemble as a whole stronger. Imagine that a bunch of students go to college, and some of them really focus on the throat, and some of them really focus on the digestive system, and some of them really focus on the circulatory system, and they emerge from medical school with different strengths. And then you have a weird disease that no one knows how to solve. Would you want a panel of doctors that all had different strengths, or would you want a panel of doctors who were all expert, who had all studied general medicine? Yeah, what I'm kind of suggesting is, hey, if they all have some weird strengths, that tends to add strength to the ensemble. And so because each decision tree is trained with a little bit of random extra emphasis on some of the patterns and a little random less emphasis on other patterns, that kind of makes these trees specialize in some parts of your data. And so as an ensemble, maybe the ensemble is stronger because we bootstrapped the training data. So ultimately, no tree in your ensemble will see your training data. Every tree will see a resampling with replacement of your training data. And then after they're all trained, then they all get to vote, and that's called aggregation. And so bootstrap aggregation is an ensembling method that is really effective with random decision trees. You could do bootstrap aggregation with entropy reducing decision trees. It just doesn't work quite as well as it does with random trees. All right, we've built a lot of trees so far in this class, right? I mean, we started with sorting trees because we use the tree set to do to keep track of states where we've been to and where we haven't been to. We've done trees for possibility trees with Minimax and with utility theory. These are trees that we could go this way or we could go that way or both ways and things like that. We've talked a little bit about taxonomies. The taxonomy tree is where you say, hey, this belongs here and that belongs there, and you're kind of categorizing things into groups. Do you know what an ontology is? An ontology is a type of tree where you take a complex concept and you start breaking it down into smaller components. There's probably also hierarchies. For example, in a business, you have the CEO at the top and then the senior executives under him and middle management, and then at the lowest level, you have all the peons that are underpaid and keep the company working. There's a hierarchy tree. And what's a decision tree? Well, it's another type of tree where you're asking questions and you're ultimately arriving at a decision, right? You need to, as you run down the tree, you're trying to figure out which side of the division you're on. In some ways, all of these trees are similar, and in some ways, they're all doing totally different things. But you see how it's just kind of a really useful data structure, right? Lots of different things are trees. I don't want you to get the impression they're all the exact same thing. They're all different uses of trees, but it seems like intelligence organizes nicely into hierarchies, and so this seems to come up a lot in AI. What I want to do right now is build an ontology tree, which is not the same thing as a decision tree, so don't be confused. I'm not doing a decision tree now, I'm doing an ontology, because I'm going to talk about how intelligence breaks down. So I've done this before, but I want to show you how these things all fit into it. As you know, I divide intelligence into two major components, which I usually call knowledge and wisdom. And knowledge is earned through is gained through a process called learning or modeling, and wisdom is exemplified, or I guess in order to, you have wisdom if you are effective at decision making or planning. It is often said that knowledge is the domain of science because science is all about facts and knowledge and what's true and what's false. Wisdom, to a large extent, is the domain of religion, right? Religion tries to tell us what's good, what choices to make in our lives. We've focused in this class, ironically, over on this half of the tree so far, right? We've talked a lot about how to plan, how to make decisions, and so far some of the we've discussed, you got to have priorities or goals, objectives, priorities or preferences at least, right? So when we did A-star search or uniform cost search or breadth first search, we started by having some type of a goal, right? And it wasn't necessarily a point, but we at least had to identify when we had arrived at our objective. In the case of utility theory, we had to know what constituted better or worse. Okay, and we've more recently started talking about game theory and how, if we try to maximize the global objective, that's more effective in general for society rather than if you only maximize your own personal utility and things like that. There also needs to be some way to optimize or maximize your utility. Primary method we studied is utility theory, which basically means do math to maximize your goal or your objective or your priorities. But we also have used a lot of different techniques, right? There's somewhere over here, and I guess you could even branch off of that and say, hey, uniform cost search and A-star and breadth first search, these are all variants of ways to maximize your goal in certain contexts, right? There's one called D-star light. Anybody heard of that one? It has some properties that A-star search doesn't have that it's kind of nice, but it's more of a pain to code up, so I didn't have you do that one. Then, let's see, somewhere over here, there's a lot of optimization techniques. I don't know where to put it. Some optimizations techniques we talk about is genetic algorithms, right? And then we talk about particle swarm, bees and ant colony. There's all these optimization techniques. I'm not sure exactly where they fit because these methods can be used to plan. They can be used to maximize your objective. They can also be used for other purposes too. So these kind of belong in a toolbox somewhere. And these are a set of tools you can apply for many purposes, but we've sort of used them over here for decision making. It turns out that there's a modeling method called a neural net. And a neural network takes inputs and produces outputs, and it has a set of weights in it, right? And we actually used a genetic algorithm to optimize the weights of a neural network to represent a policy to represent your plan or your decisions, right? So we've actually used neural networks over here on the side of planning. But neural networks are also often used for modeling, so they generally belong over here on the knowledge side of the graph. I guess therefore neural networks probably belong in the toolbox of tools you can use for multiple purposes. But for right now, I'm going to consider a neural network to be a modeling technique because we can use it to model all kinds of things. Where do you suppose decision trees fit into this tree? The word decision has the same word in it, doesn't it? I feel like a decision tree is a model. And so this is where we need to see what's going on and see if we can understand how these things all fit together. Do you remember with the neural network, I talked about how you have these set of features that are fed into it. We could just call them inputs. And it produces some predictions, which I usually call labels. And so the neural network is really a function approximator. You could say it's a function of features and weights, where the weights are the guts inside of the neural network that affect what function it represents. But ultimately, a neural network maps from a set of features to a set of labels. With me? What is a decision tree? But the whole reason we have a tree is because we're going to feed into it some set of features and we want to get out of it some set of labels. And you see how really a decision tree and a neural network are providing the same operation. They're mapping from some inputs to some outputs.